Okay, so thank you all for joining our meeting. It's a great pleasure for me to introduce our speaker today, who will talk to us about elegant host-side wrappers for Cuda API. Eyal is an author of most popular Cuda API wrappers library, which we should all be interested in because it's an excellent way to make our code both safer and faster. Before we start, I'd like to discuss a few organizational questions. So I'll be recording this presentation. I'm going to turn off the recording as soon as the presentation ends, so feel free to discuss any Cuda-related questions afterwards. Our meeting will last as long as we have subjects to discuss, so don't hurry to disconnect. And that'll be all I wanted to say, so please join me in welcoming Eyal.
So thank you, Grigori. And I would like to share my my presentation, but it's telling me that okay, now I can share it. There we go. So hello again to everybody. It's a pleasure to be with you in the Cuda community meetup group that you have here. And yeah, I guess one of the benefits of doing things virtually is being able to host people from faraway places. So I hope you're all doing well in these still trying times of COVID in Russia as well. And like Grigori said, um, we're going to be talking about writing more elegant CUDA code, but not the kernel side, but the host side code in modern C++. This is not actually not a session for advanced users. I'm just going to assume that you're generally familiar with CUDA, that you've written a kernel or two in your life, maybe also the code that launches that kernel, and that you have some C++ experience. Certainly, I'm not targeting any experts. And that's basically it. But later on, during the Q&A or discussion part of our meeting today, then we can dive in deeper into the finer points of things as far as you like and as far as I can accommodate. By the way, I know that the people's microphones are muted right now, but if anybody has a question, then do feel free to signal somehow, like maybe put something on the session chat or whatever, and I'm perfectly willing to stop and explain things. In fact, once I get to a certain point, I will ask that for just a bit of feedback here and there. So be ready for that. So what are we going to do today? I'm going to recap a few of the issues, at least the issues that I have with the host side API that Cuda offers. And then we're going to look at a specific program in Cuda, which actually you might already be familiar with because it's pretty famous. And then we're going to gradually transform it. So we're going to make a sequence of transformations. Some of them will some of them will involve my wrapper library, and some are more generic or even trivial. And we're going to look at the differences between subsequent versions. So we're going to move from the initial version and transform it again and again. Every time we'll see what changes we've made. So we're not going to change everything at once. And we'll think of the rationale and the benefit, if it is always a benefit, in every transformation. And then we'll have another fine look at our resulting program and hopefully appreciate its elegance. And like I said, it's a free-for-all in the Q&A part later on. Okay, so Cuda's existing API. I'm talking about the Runtime Api. I don't have a slide for this, but as many of you may know, there are two, shall we say, levels at which you can interact with Cuda. One is interacting with the Cuda driver, the kernel driver. And another layer, which is what most of us use, has a slightly higher level of abstraction, and it's called the Runtime Api. And in a sentence, the problem with it is that it's extremely C-like, even though it's not technically all C. So, for example, all of the API calls return a status indicator or result indicator. And that means that whenever you make a call to anything, and we'll see this later, you have to check the return value. And if you don't do that, then instead you have to write some kind of a macro. So maybe you've seen this kind of code or maybe you've even written it in your own programs or seen it on Stack Overflow or places like that. So this is a macro that calls a check for the return value, and if it fails, then it writes an error message, and that lets you wrap calls and make sure that they return correctly. And even if you do use that, and you don't mind a little macro ugliness in your life, then you still have the problem that you can't chain your calls. So you can't do something like this. This is just pseudocode. It's not necessarily something that's supposed to work anywhere. But you can't say, okay, I want my current device, and then I want the properties of that, and then I want the compute capability out of those properties, and then I want the major number, because the compute capability has, say it's 7.5, then 7 is major and 5 is minor, then I want the major number. So I can't write this in like a single instruction. It'll have to be half a page of code, almost. So that's one thing I dislike. And another thing that has to do with both with convenience but also with safety has to do with resource allocation. In C++, there's this concept called RAII. Resource allocation is initialization. Some people know it as constructor allocates and destructor releases. But we don't have that with the Cuda API. So if we're allocating memory on the device, or we're creating a stream, or we're creating an event, or we're using other code that has state, maybe at the driver level, which I won't get into, then you always have to remember to release those things when you're done with them, but not only when you're done with them. Even if you say you have a failure somewhere in the middle and you want to exit, you can't just exit your function. You have to make sure to release everything that you've used. And if you have some code that throws an exception, then you're actually in quite a bit of trouble, because the exception will leave your current scope without you having had the possibility of releasing what you need to release. So that's not very pleasant. And another point has to do with naming. So if I can go for a second to the Runtime Api. So this is the official documentation on NVIDIA's website, which you probably have had a chance to look at from time to time. The API obviously has a lot of functions, but since they're all C-like and there are not that many, when there isn't a division into namespaces or contexts of classes, etc., then it's just a huge list of functions that you need to remember. So just for example, if you look at, let me scroll down here for a second, this huge block of stuff, these are all of these have to do with memory copying. So you have to know something like what and there are other functions elsewhere. So I've counted up to 19 functions that have to do with memory copying. And sometimes, even though they say what they do, it's not exactly clear just from reading a single function name what exactly it's going to do. So, for example, if I'm mem copying to array, does that mean that my source is also an array? Because I also have functions called memcopy to darray to array. So that's a bit confusing. And even if it's not confusing, I'm never able to remember all of these by heart. And there's more where that came from. That's just a prominent example. And another thing that also has to do with catching errors is that there's a lot of use of numeric IDs. There are indices of devices and or peers of events, and sometimes it's you do catch things because the type is different because it's a different kind of pointer. But if it's just a number, there are a lot of just ints floating around in your CUDA code typically. So good luck not mixing these up. And and this in itself, so there are lots of APIs in the world. Sometimes they're kind of rudimentary or low level, and I might not have been driven to do something about this, except for what we know about the device side. So if when you're writing actual kernels, which we will not do at all today, then this has been very like up to or has been catching up to modern C++ over the past decade. And it's very common to see use of templates, to see namespaces, classes, references, and even more modern versions of the C++ standard are gradually being supported. And over the past few years in versions of CUDA, we've even seen the latest version even has some C++ 17 features, and that means that by now you might already be used to, when you're writing kernel code, uh, to use ranged for loops or lambda functions, or to do more of your computation in compile time, which is actually pretty useful in terms of performance. But on the host side, where it's like we're stuck in the 1980s. And there's definitely, although I will say that that on the host side, on the device side, the writing templated kernels is not perfectly supported, and you might want to ask me about this in the discussion section of this session, but that's not what we're talking about today. So we have a very nicely C++ified device-side code or device-side aspect of CUDA, and the host-side aspect has been left back. So this kind of annoyed me, and I mentioned earlier before the recording that I was working at CWI Amsterdam on some database acceleration business a few years back, and I found myself writing several wrapper classes for memory allocation and for streams and for devices. And at some point, there was just I've amassed enough code that I decided to complete it into something I could release as a library. And this is what I'm talking to you about today. So you don't have to write down the URL or anything. And plus, it'll be up on the screen again when we're done. But it's on GitHub. The library is for C++11, and the intention is to make it as usable as possible. Even though with newer versions of the standard, I might have had another feature here or there. The focus is on its being lightweight. So differently than there are other ways to use CUDA which are at a higher level of abstraction. So for example, if you know about Thrust, it's a library that offers you a model of writing code that's a bit similar to the C++ standard library, and has the equivalent of the algorithms in the standard library algorithm header. But you really, it forces a sort of a discipline on you. You have to use its own data structures, and you have to work the way it expects you to work. And my thought was to constrict the user as little as possible, or rather just provide the exact same API that we have from Cuda, that is more C style, to make it C++-ish, and let you use the same thing on same things on the same level of abstraction, but in a more language-friendly and developer-friendly way, I hope. And it's a work in progress. It's definitely not perfect. For example, there are things that are in the API that I don't support. And one example is in the interoperability with graphics. It's not that it would be difficult to add. It's just a matter of, because it's something I don't work with myself. I don't really feel confident enough to write that. But if any of you does, for example, do work on graphics and is interested in extending the wrappers in that direction, that's very possible. They're relatively modular and not difficult to work with. It's not a very arcane code. And maybe later we'll even look inside, like under the hood for a bit. Okay, so after the more introductory part, it's time for us to look at some code. But before that, if there's any question, something that has not been clear enough this far, then this is the time to ask before we go into dive into some code. And Yogi, okay, if you want to turn people's mics on just for a brief minute, then let's do that in case somebody wants to ask a question.
I suppose they could unmute themselves if they want
okay.
to. So
okay.
I don't see any questions in the chat. So I suppose we could continue.
Sure. Okay, so what you should be seeing on your screen right now is a utility called meld, which shows the difference between two files. In our case, it's two Cuda programs. So before looking at the first changes that I'm making, let's just look at the left side here. This is actually, I said you're probably going to know this program. This is one of the first example programs that many people learn Cuda with, which is a program that adds up two vectors element-wise using Cuda. And it's part of the Cuda Toolkit samples. So let's just go over it real quick to remind ourselves, and then of what's in it, and then we'll start messing with it. So the first part, and this is, which in a sense is the core of the program, but something we won't really be looking into, is the kernel. So this is the kernel that adds the elements of B to elements in A and puts the result in the array C. And like I said, not going to be talking about that because our session is not about writing kernels at all. There is some helper code that I'm not going to, also not going to get into. There's the Cuda Runtime Api header that we will definitely, we have to use. And now let's look at the main program. it starts with some memory allocations on the host side, and everything has to be, and you'll note, you're noticing it's all very C-like. Everything has to be verified that the allocations have passed, and then they're filled with random values, and then that's that part. Then we're doing the corresponding allocations of memory on the Cuda device. So this is global memory using the Cuda malloc call. So here's buffer A, buffer B, and buffer C. After that, we're copying from A on the host side on the host side to A on the device side, and the same thing with B. Then we're configuring the kernel launch. So we're calculating the number of blocks and the number of threads, and this is the kernel launch line with the triple chevron. And notice that with every Cuda API call, we're checking for errors. So we're seeing a lot of these blocks if error is not Cuda success. The same thing after the kernel launch. And then we're copying the result back from C on the device to C on the host. And finally, we verify that the resulting array is what we expect it to be. So we're checking that the sum of the values on the host minus the value that we got from the addition on the device is close enough to 0. But this is the program is not over, because then we have to free everything. So we're freeing the memory on the device and we're freeing the memory on the host, and then we're done. Okay, so the first sets of changes I'm going to make are just going to be some housekeeping, so nothing to write home about. So if you now look at the right side, the program on the right, you'll notice that I'm removing the print instructions. So none of the printfs, at least for now. So those are all gone. And this is the first change I've made to the program. Not very interesting yet. Now whenever I switch windows to the next version, so if before we had the first version and the second one, now we have the second one on the left, and the next version, they're all indexed, so the third version of the program on the right. Now I'm taking a lot of the code that you've seen here, and I'm putting it into a header called notinteresting.qh, so Cuda header. So what's going to be not interesting for us? The copyright notice, the comments, the kernel, and what else? The comparison of the results, all of that stuff goes into a header file because I'm not talking about it. Okay, now the next change after the not interesting part. I'm going to change do something that's more in line of how I would write the main program in C++. So no need to return 0. By the way, this has nothing to do with Cuda yet. You never have to return 0 from main. If you just finish main, then you're returning success. So another uninteresting change. Now things are starting to happen, even though we're not working with not the Cuda part yet. But it's that you're going to notice that things are going to kind of echo each other. So bear with me. The first thing I want to do is I don't like the manual C style allocation. So I'm going to use smart pointers, or specifically the unique pointer facility that exists in C++ since C++11. Although this specific call is actually dependent on C++14. This is std make unique, where you give it an array type and the number of elements, and it creates a unique pointer with that many elements of the type you chose. And when we do that, we don't have to check for the errors because it's going to throw an exception if anything fails. Now, you'll notice that before we were checking for failures here, and later on we never when we noticed some kind of failure with the CUDA calls, we did not free the allocations, and that didn't really matter because we're in the main program. But if this was all some function, so if we called it an add vectors function, not that it's a very useful thing to have, but suppose that we were to make this a function, then that would be a memory leak, because all of the memory we allocated here would be gone if we just exited when we noticed the CUDA error. Once we move to unique pointers, then when we leave the scope, regardless of whether we're exiting or whether an exception is thrown, then these will get released. And we'll want to do essentially the same thing for the CUDA allocations as well. So we're gonna see how this happens in a while. But just that we go through the changes now, because these are unique pointers, to get the address, you have to call the get method. So you're seeing a few changes here where we've swapped out the use of the pointer with calls to get, and no more freeing. Okay, next change. And I said this is now it actually gets interesting. First, we have a new inclusion, and this is an inclusion from the API wrapper library. So we're including this actually includes all of them. We could have included less. It's a set of headers. Some of them are codependent, and there's also a general one which includes all of the headers. It's not a huge amount of source. It's self-contained in the sense that it doesn't take anything from Boost or anything like that. It only depends on Cuda's headers itself. So taking all of them is okay-ish. It's not it won't blow up your compilation time. And now that we have that, let's do about the same thing that we did with the make unique. Let's do it with the global device memory. So if I weren't, you're already seeing how it looks like, but suppose I would have told you, I want something like make unique, but for CUDA. So instead of std make unique, I want some sort of a CUDA make unique, which looks the same and has basically the same semantics. And it turns out that they can just do that. It's not extremely difficult to code. There's some finer points, but it's very doable. So it's not CUDA make unique, it's CUDA memory device make unique. Why the extra namespaces? Because, well, first, because I don't like how the standard library only has one namespace for everything. So in the API wrappers, there's Cuda Memory, and there's Cuda and Stream or Cuda Device for functions that have to do with streams or with devices and are not part of the class. So there's sub namespacing. But also when it comes to memory, we have different categories of memory in CUDA. There's global device memory, which we can allocate. There's host side memory, but that's pinned, which means it's directly mapped to places in actual physical memory, which makes transfer faster. So you can do, for example, Cuda Memory host make unique, and that will also work. So there are several things you can put here instead of device, but we're allocating global device memory, so that's our namespace. And make unique works exactly the same way. And it gives you a unique pointer. It's not the same type as std unique pointer. It's very close to it, but you don't even have to know what the type is. It's actually std unique pointer with a custom deallocator. But your programming doesn't depend on it. And we're actually, part of the design rationale of the library is that you should be able to use auto a lot when you don't care about what the type exactly is. But the calls are not exactly the same, because on the host, we just gave the number of elements that we allocated. But here there's also a device. And we need this because we have to say which CUDA device we're allocating on, because on each system, there could be multiple devices. Unlike in the Runtime API itself, you usually set the current device. So you have a global state, which is the current device. And a lot of the calls are just assume they work on the current device. I tended not to take this approach, although here I do take the current device. So this call, like I said, there's a sub namespace for device related code. And this is for code that has to do with the current device, and this gets a device. And again, never mind what the type of that device is. It's not an int. It's not like an integer handle. Don't worry. But now we have the current device, and it's in some sort of an opaque type, and we pass that type to make unique. But you won't get it wrong. So for example, if you were to write int device 0, this wouldn't work. It will tell you, I need a CUDA device. Let me even try that. Never mind. Maybe we'll do that later. So you do have to wrap it, but you could say, for example, auto device equals CUDA device get 0. So this would work. And that will get the first device on the system, the second device on the system, etc. So it protects you from mixing up numeric constants with identifiers of things. Anyway, so once we write that, we can get rid of this part of the code. So the payoff in this session is that we're deleting a lot of code that's on the left. And like before, since it's a unique pointer, then we're using the get method. So there are a few changes that have to do with that. And also, these deletions don't have to happen explicitly. This is all implicit. And again, I'm reminding you that if we were writing a function and we caught some sort of an error, then when we leave the function, then our global memory would be freed. And this is safe. So if we've messed up the state of CUDA somehow, which can happen in certain cases, then we won't get a double exception or anything like that. So just to lay your worries to rest. So this is our first proper transformation that actually uses the Runtime API. And I should mention that whenever I show you a program, it's a working program. So now if I quit this, close without saving, and now so this is the version 6 that I just showed you, and I've copied it to be vector add.q. If I now compile this, So I'm using NVCC, I'm compiling the coup file into an object file and then linking the object file into an executable. So I've removed all of the printouts, but except for the case of errors. But if there had been an error, we would have gotten a message. But like I said before, so every transformation results in a working program, just so you know. Let's go on. So we are done with the allocation. Now let's take care of copying. I want my copying to be simple. Let's have a copy, sort of like STD copy. Not exactly, because it doesn't take iterators. The wrappers don't have a concept of an iterator, and that's because the Runtime API doesn't either. So even though I've kind of rounded out the abstractions that the Runtime API has and made them C++ like, I haven't really created anything that doesn't exist, that's not part of the API. So what we're using here is pointers. So we're copying from the host side buffer to the device side buffer. This is the size in bytes. And this will, and Cuda's Runtime API is able to figure out the direction of copying. So we don't have to specify Cuda memcopy hosted device. And this is not something I did. The Runtime API itself can look at pointers and know whether they're on some device or whether they're on the host, and it uses that to do the copying. And the copying is also protected in the sense that if there's a failure, so you see the error check here, this happens on the inside. If the copy fails, then we're going to throw an exception. I'm not catching exceptions in this program explicitly, so they would make the program crash. Or if we were in a function, they would propagate upwards where you can catch them. And when you catch them, in addition to some description of what failed, you will have the Cuda status. So this thing also has an associated string of what kind of Cuda Runtime API error this is, and that goes into the exception that gets thrown. So that's the copying from the host side to the device side, and this is the copying in the other direction, which looks exactly the same. And we're done with the copying. And now on to the next phase, or the next transformation.
I just have a quick question.
Sure.
You mentioned that the APIs, the runtime APIs are able to figure out just sort of the pointer type on their own.
Yes.
And is that true even if the host pointer wasn't allocated using Cuda host alloc?
Yes, it does. And in fact, in this case, that's what happens, because this is just a standard library allocator. It doesn't do anything relating to Cuda. And the reason is that there's a single 64-bit address space, and Cuda's driver arranges it so that, or kind of interacts with the operating system or the processor, and to make sure that its pointers have a certain range, and pointers that are allocated in actual memory or in the process's virtual memory space on the host side are in a different range. So it could look at a prefix, like the higher bits of the address. Maybe it's a byte or 2 bytes, I'm not even sure. And it can know whether to which device it belongs even.
Okay, thank you.
And but since you asked, I'll show you. So if you look at the underlying, or one of the possible underlying functions, an actual Cuda memcopy, then you have the kinds where the copy kinds where you specify the direction, so host to device or device to host. But there's this the default, which lets the Runtime API decide. And this requires unified virtual addressing. But this has been a feature of hardware, the hardware since I think Kepler devices. Yeah, I think since Kepler and since Cuda 6, if I'm not mistaken. So if you go back very far, then that wasn't available. But the API wrappers formally support Cuda 7 and later.
Okay, thanks.
Okay, onwards. Now let's talk about launching kernels. And before I show you, or we go through this transformation, I just want to mention that the examples that I show you are not just, they're not all there is to the wrappers. And even when it comes to allocation or copying, there's the wrappers have more. So you can definitely do allocation that is not within the scope of a unique pointer. There's wrappers for that are that check for errors. For copying as well, there are different kinds of copies between different memory spaces. Or there's mapping that has to do with managed memory, and of course we're not going to put all of that in a sample program. But I just wanted to emphasize that this is not the only way you can work with the wrappers. And this is especially true for launching kernels, because when we launch kernels, we can just we can launch them mentioning a device, or we can enqueue them on a stream, which is also true for copying. So here I just did a synchronous copy, but obviously you also want to be able to do an asynchronous copy, but that works through enqueuing a copy operation on a stream. Anyway, kernel launches. So I divided this into two parts. The first part is creating a launch configuration. So the wrappers have a launch configuration class, which has a named constructor idiom called make launch config. It has a few variants, but this variant just takes a number of blocks per grid and threads per block and creates a launch config object. And the calculation is basically the same, but I'm just illustrating here that I have some convenience types which represent different numeric values. So there are grid dimensions and there are block dimensions, and it's not there's nothing special about them. Eventually, they're just different kinds of integers. But it does make sense if you have like a signature for a function and that takes the size of the shared memory that your kernel needs. Then it is going to be just a number, but you can give it a type name, something like Cuda Memory shared size t or something like that, and that at least helps when you're reading the function declaration better understand what the number means. Anyway, so we have our launch configuration, and here's one way to launch kernels with the API wrappers. So the device object can do a launch. So this is, but there's also a freestanding function that can take a device and launch on that device. Here we use the launch method, and this method takes a kernel name, a launch configuration object, and the kernel arguments. So obviously this is a variadic templated method, which has a variable number of arguments here. But the launch config is a wrapped object, so it's not like you have to type in the numbers for the launch configuration and then switch to the first argument, which can be confusing. So this has to be from an object of a certain class. And no triple chevrons, fortunately. I don't like those. And this is essentially the equivalent of this part of the code. Now, there is error checking here, So if you've entered an invalid number of blocks or size of a block, then you will get an exception. But you should know that checking for errors when you launch the kernel does not mean that the kernel concluded successfully. Neither on this side nor on this side. It's only if you do a synchronization that you can be sure of that. But we'll get back to this a bit later. Anyway, now we have a launch method. And here's our copy and our verify correctness, which makes a call into the not interesting part. And that's, so we're done with this transformation. But I'm not done yet. Okay, so after we've replaced the code for allocation and copying and launching and copying back, then everything that we do with Cuda now has the potential errors checked, except for the synchronization, which didn't exist in the original program. But now I no longer need to keep this this variable that I was using to check for the status. So that's gone. Next transformation. So in the next transformation, this is again not so back to making changes that are not related to Cuda in themselves. So we had this this loop that initialized our data. We can actually use one of the algorithms. So this is something that was already available before C++11, but its use is definitely recommended. But now we can also use it with lambda functions. So what we're doing here, so the function that we're using to set A and B is return. Oh, is it exactly the same thing? Oh, it looks like I changed the semantics a bit. Okay, so you'll have to excuse me. I changed the distribution a bit, but never mind that. The point is that this is a function that that returns a random value in some range. Here, the range will actually will be between 0 and 1. And we can use the generate algorithm to set the values of all of the array. And I don't have an equivalent for this in the API wrappers, because obviously that's not part of the Runtime API. But I do have something like this in a different library that I'm not mentioning right now. The point here is that that with this change, this removes the last loop that we were using anywhere, and also the last condition we were using anywhere in our program. And if you look at the program we have here, then this is a program with no loops and no condition checking. Of course, conditions do get checked in within functions that we call, but the logic of the program is now much clearer, easier to read through. Plus, it all fits on a single screen, which is nice. But I'm not done yet. There's still some more to go. So a bit more house cleaning. In not interesting, I created a div rounding up function for computation here, but that's not very interesting. So I'll just skip right on ahead. Another point, since we're talking about writing more elegant and modern C++ code, before we were using the rand function to generate our random values. Actually, the rand is a really problematic function in terms of its distribution, which is not really uniform. Well, it's not just that it's not really uniform, it has certain weird skews. And there's an interesting talk that that you might like to catch if you haven't seen it, by Stephen Laveve, who's the author or the maintainer of Microsoft's standard library implementation. And he has a talk about why you should never ever use rand. And instead, we have facilities in C++11 for generating random values. And I suggest everyone use them if you're not already using that. And these facilities, what they result in is an object which is a distribution, and you sample from the distribution by passing it a randomness engine. And the distribution I choose here is between 0 and 1, and that means that when I sample from it in the generator function, it's very similar to taking 1 and dividing it by a random integer. So another transformation to make our program more C++ clean. And this is in the random header. What do I have for you next? Oh, this is just a comment. Okay. So before I was telling you that just by launching the kernel, we are not actually certain that that the kernel concluded successfully. That's not really a problem, because the synchronous copy will not succeed if the kernel had failed, because of the dependency between them. So if the kernel that we wrote somehow had an error, like maybe it accessed some memory that wasn't allocated to it, then we would likely catch it in the copy call. So this would throw an exception. And now I want to do things differently. So I do want to have a synchronization, but I also want to show you a different way to launch a kernel. And this time we'll do it asynchronously. We're not going to have some very complicated synchronous program, but we will need the stream. So in Cuda, we have streams, which are actually queues for tasks for the GPU to execute. And Q is actually the name of the corresponding object in OpenCL, for those who know OpenCL. And this is a way to create a stream, not the only way. So if we have a device object, we can create a stream on that device and pass it some flags, or no flags, that's also possible. But we can also just make a stream using a standalone function, and then we need to pass the device and the flags if we want them. Also the priority, because streams can also have priorities. And this is a constant. So one of the things I have a lot of in the API wrappers is Enum Constants, which correspond to the namespace key. So if you do Cuda double dot stream double dot, and you have a completion feature in your IDE, you're likely to get some of the different constants that have to do with streams. After we've created that stream, instead of launching the kernel on the device, which will mean synchronous launch on the device's default stream, we are enqueuing it for launch on the stream. So a stream object has a sub-object called enqueue, and the methods of enqueue correspond to the different things that you can enqueue. So you can enqueue a copy, you can enqueue an event, and we'll see that as well in a few seconds. And you can enqueue a memset or mem0 even. And of course, you can enqueue a kernel launch. Oh, you can also enqueue a callback function to execute. Anyway, we're queuing the kernel launch. The syntax is very similar to device launch. So the name of the kernel, the launch configuration, and the arguments. And this is how we synchronize a stream. And this makes sure that this completes all of the commands on the stream so far. And if there were any errors, then this will throw an exception. And once we do that, if there were any errors in the kernel, then we'll catch them here rather than in the copy. Any questions about how I use the stream? Okay, so there are only a few more transformations left, and they will involve a bit of timing and use of events. Okay, so I have my stream from before, and I'm going to do timing using two Cuda events. Not because this is a very useful way to time kernel executions, and actually it's not extremely accurate, but it works. So, and it's a good opportunity to use events. So here I'm creating two events. Events are specific to a device, but they're not specific to a stream. You can put them on a stream, but when you create them, it's on a device. So here are two events: before kernel starts and after kernel starts. And I'm going to enqueue them so that their name makes sense. So first, I'm enqueuing the before kernel starts event. Then I'm enqueuing the launch of the kernel. And finally, I'm enqueuing the after kernel ends event. And I'll also mention that you can also, another thing that you can enqueue is not exactly an event, but making another event fire. So if you have an event on another stream that's called, let's call it E, and you enqueued it on some other stream, stream 2, and maybe you're waiting on an event on that stream. I'm sorry, so what you enqueue in stream 2 is waiting on an event, so you can enqueue a wait on another stream and then have the event occur on this stream or the other way around. And that's the way you, like in the Runtime API itself, you create dependencies between events on or actions that you want to take on different streams. Anyway, this is simpler. It's just a single stream. And with these three events, when we do the synchronize, just like in regular Cuda Runtime API, this makes sure that everything has happened, the two events, and both events have time. And so we have a function in the API wrappers that takes two events and returns the time that elapsed between them. And the time elapsed actually uses std chrono. So beginning, you don't see it here because it's included from within the Runtime API, but the standard library has time facilities, which probably most of you know about. But just as a reminder, date and time utilities. So it's a sub-library of the standard library, and it has clocks and time points and durations. So we're actually using a duration. The duration class is templated on the underlying types and what's the period of the ticks of the clock, and we're not going to go into the details, but the point is that this actually returns the duration or what we get from the Runtime API is the duration in milliseconds as a floating point number. And this is what I'm printing here. So if you have a std chrono duration and you take count, that gives you the raw value that's within that duration. And let's just see it in action for a second. happened to my what happened to my print? Weird. Okay, weird glitch. Anyway, then the Runtime API wrappers does the bridging between the Cuda API and the standard library here. Why did this not happen? Strange. And with this, sorry. And this is in fact the final form. So we've covered copying, allocation, devices, streams, and events, and of course kernel launching. This is a big chunk of what the Cuda Runtime API is about. It's obviously not all of it, but this gives you an idea of how code looks when you use the API. And a sense that I wanted you guys to have is that, and that's also why I kind of interchange the transformations that are CUDA related and not CUDA related, to see that the spirit in which we tend to write code with the more modern C++ versions is very much the spirit I wanted to have with the Runtime API wrappers. And I hope this seems useful and enticing enough to get you to try it, and hopefully enjoy it, and maybe give feedback. And with this, I'll yield the microphone back to Georgi, and we'll continue to the questions, answers, and discussion section.
Thank you a lot. So it was a great talk and quite useful library, because maybe 2 weeks ago I started using it in every project of mine, except like working projects. So it's really something that you could write yourself. So I found myself writing a few of those wrappers, and it actually helps to have it in one place. So I'm going to stop the recording